can get started now. So this is our second to last class, and in this class and the next one, we're going to be talking about infinite sets. So let's just get into it. So you guys might have, I don't know what you guys have heard about infinity, but a lot of times people will say infinity is a concept, not a number. And that's true. Infinity is not really a number. You can't write it down. You can't really treat it like a number for a variety of reasons. But here, using set theory, we can try to get an understanding of what the concept of infinity is. And to do that, we're going to think of infinite sets, or sets that have infinitely many elements. And a few examples that we've already talked about are Z, which is a set of integers, or we have N, which is the set of natural numbers. And you'll remember that whenever I describe these sets, I have to write ... to describe them because it has an infinite number of elements. So I can't just write all the elements. And so we're gonna talk about what it means for these sets to have infinitely many elements. So remember, the cardinality of a set is the number of elements in the set. And if we're going to be talking about infinite sets, it's going to be helpful to think of cardinality, because what we're really talking about is the number of elements in the set. So let's think about the cardinality of the natural numbers. So that's going to be written with those two bars around n. N does have infinitely many elements, but we cannot just write infinite. It's more complicated than that, as most things in math are. So we write the cardinality of n, the natural numbers, as aleph null. It's this Hebrew letter aleph, which looks sort of like an n, a little more stylized. And then it has a subscript 0. And this is aleph null. This is the number of elements, or the cardinality of the natural numbers. So as we're going to see later on, not all infinite sets have the same size. So some infinite sets have more elements than other infinite sets. And here aleph null is the smallest size that an infinite set can have. So later on, we'll see a set that has size aleph 1, so that 0 will become a 1. And that is going to have a greater size, a greater cardinality than aleph null. And sets with cardinality aleph null are countably infinite. That means we can count or list the elements. So even if you can't, name every single one, you can show a way to list them. So if n has cardinality aleph null, do any other sets have the same cardinality, aleph null, or any other sets countably infinite? So in general, if we can demonstrate a mapping between the two sets, which means showing a correspondence between every element of one set and every element of another set, then we know that those two sets have the same number of elements or the same cardinality. And we can do that with infinite sets. If we can show a way to correspond every element from one infinite set to another infinite set, we know those two sets have the same size. So this is an example on the left with some finite sets. So set A has elements x, y, z, and w. Set B has 1, 2, 3, and 5. We can map x to 1, y to 2, z to 3, and w to 5. And because of that mapping, we know that sets A and B have the same number of elements. So another example, where the natural numbers are 1, 2, 3, and so on. And then the whole numbers are the same thing, except they start at 0. And we can map the natural numbers to the whole numbers by subtracting 1 from every natural number. So what you can imagine is if we have the natural numbers like 1, 2, 3, 4, 5, and then we subtract 1 from each of them. 1 goes to 0, 2 goes to 1, 3 goes to 2, 4 goes to 3, and 5 goes to 4. And we do this forever. Well, forever. And in this method, we've shown that we can map the natural numbers to the whole numbers, and thus, even though the whole numbers have 0 and the natural numbers don't, the natural numbers and whole numbers actually have the same cardinality. And it turns out that there are a lot of sets that have the same cardinality as the natural numbers and the whole numbers. We can also map the natural numbers to the integers. One way you can do this is by imagining the natural numbers as the evens and the odds. So we'll put the evens over here, 2, 4, 6, and then so on. And then we'll have 1, 3, 5, and so on. And then we can map the evens to the negative numbers, the negative integers. And this will be -1, -2, -3, and so on. And then the odds will go to 0 and the positive integers. So that'll be 0, 1, 2. And so in this way, you can see that, again, we've mapped the natural numbers to the integers. So again, the natural numbers and the integers have the same number of elements. Lily asks, can infinity be considered an estimate? That's an interesting question. I would say that the concept of infinity, as we've outlined here, it's very precisely defined. So we know exactly what it is. The math to define all this is a little more complicated than what we're doing here, but we definitely know what infinity is. It's just that it's so big that it's infinite. So it's like as big as something could be, so that just having another element, so if you have the 0, that's just one more element, so it doesn't really make a difference in the size. And then down here, just adding the negatives, right? It's already so big that just adding the negatives doesn't really make a difference in size. So maybe that helps you think about it more. Yeah. Any other questions so far? All right. So from what we've just shown, the natural numbers, the whole numbers, and the integers all have the same cardinality, and that cardinality is Aleph null. So even though the whole numbers have 0 and the natural numbers don't have 0, and Z has 0 and all the negative numbers, and natural numbers do not have those, all of these sets have the same size, and that's because infinity is weird and it does weird things in math. So later on, we are going to see some sets that actually are bigger than n, that have a larger cardinality than n. But for now, we just have these countably infinite sets. So we're going to do some practice with them. So try and find a mapping between n and the positive even numbers, so a way to correspond every natural number to every positive even number. And because you can make this mapping, so after you make it, what does that tell you about the cardinality of the set of positive even numbers? So I'll put in chat if you get a mapping, and then we'll talk about it. Remember, a mapping is just a way to correspond every element of n to every element of the positive even numbers. Gonna wait one more minute. I want to see a couple more people give guesses, some kind of answer. And for those of you that have figured out a mapping, what is the cardinality of the even numbers? All right, let's talk about what the mapping is going to look like. So if we have our natural numbers, 1, 2, 3, 4, 5, 6, so on. And then we have our even numbers, our positive even numbers. That's 2, 4, 6, 8, 10, 12. So you can actually just look at these two lists, and just by listing them, we have made a mapping. So we can map every natural number n to the even number 2 times n. So 1 is going to be multiplied by 2. That gives us 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8, and so on. And in this way, we can map every natural number to every positive even numbers. And you'll notice that really, if you can figure out a way to list the elements of a set. So here, all we did was list the even numbers, and then even though we didn't list all of them because it's infinite, we showed a mechanism to list it. So just write them in order like this. You can just do that, and that will show that two sets are both countably infinite. So with the integers, which we had just talked about, I showed sort of a mathematical way to make a mapping. But what you can also do is just say, here are my natural numbers, 1, 2, 3, 4, 5. And then I'm going to list my integers. I'm going to start with 0. And then I'm going to go to 1, and then -1, and then 2, and then -2, and so on. So I'm just going to list every integer by alternating positive and negative. So even though this isn't like a mathematical correspondence, it's another way to show that the integers are countably infinite. So if you can list something, it's countably infinite. Let's see, what is the next question? Oh, and here's the second part. As a result of this mapping, what is the cardinality of a set of even numbers? So because we showed that it has the same elements, same number of elements as the natural numbers, we know that it is countable, or it has a cardinality of Aleph null. Which, remember, let's see, we wrote like this with this Hebrew symbol Aleph. So this is our next question. Can any of you think of some sets with the same cardinality as the natural numbers? And if you do that, try to find a mapping between your set and the natural numbers. And then try to find some sets with lower cardinality than the natural numbers. And that's going to end up being finite sets. So just figure out a way to type it in the chat. And I'm curious to see what you guys come up with. So this is just sets that you can map the natural numbers to. And the ones we've talked about so far are the whole numbers, the integers, and the even numbers. Yeah, so Andy says the odd numbers, and that's right, that is a countably infinite set. Can anyone tell me how you might map the natural numbers to the odd numbers? You can do it mathematically, or you can just do the way where you list both lists and show that they're countably infinite that way. All right, so let's talk about how to map natural numbers to the odd numbers. Well, someone just showed me a way to list it. Eli gave a way to list it. So you start with our natural numbers, 3, 4, and then we have our odd numbers, 1, 3, 5, 7. Yeah, so with the odd numbers, it's not too hard to just list them. You can just write them in order, and that works fine. And then if you want to write it as an expression, write it mathematically as a function, we can say we're going to take our natural number, multiply it by 2, and subtract 1. So 2n minus 1. And so if you do 1 times 2 minus 1, that's going to give you 1. If you do 2 times 2 minus 1, that'll give you 3. If you do 3 times 2 minus 1, that's going to give you 5, and so on. And in this way, we've shown that the odd numbers and the natural numbers have the same cardinality. So the odd numbers are also a countably infinite set. And another thing you can do is you can use any countably infinite set. So you don't always have to use the natural numbers. If you know another set is countably infinite, you can use that one too. So let's say I wanted to use the even numbers instead to show that the odd numbers are countably infinite. Let's start with our even numbers. 2, 4, 6, 8, so on. 1, 3, 5, 7, and so on. So what we can do is just take our even numbers, subtract 1. And since we've already shown that our even numbers are countably infinite, then we can use them to show that the odd numbers are countably infinite. And he says the whole numbers, and that's exactly right. We've already shown how to do that mapping, but that's right. Can someone give me, this shouldn't be as hard, just a few sets that are not going to be infinite, or that are not going to be countably infinite, that are finite. Just to remember what a finite set looks like. Yeah, Eli says the set of numbers 1, 2, 3, and that's right, that's going to be a finite set. So it's good to ground yourself, remember what a finite set looks like. Not always get too tangled in the infinite stuff, even while you're working on it. All right. How about this question? Is the set 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on, countably infinite? Try to find a mapping to show.
What do you mean by countably infinite?
So all the infinite sets we've looked at so far are countably infinite. And that means that you can list the elements. You can show a way to list all of them in order, or you can show a correspondence between this set and the natural numbers. So if you can show a correspondence of the elements of one set to the natural numbers, then it is a countably infinite set. And a couple people have said, yes, this is countably infinite, and that's right. If we will just map n to 1 over n. So if we have 1, that is way too big. 1, 1, 2, 3, 4, so on. We can map 1 to 1 over 1, 2 to 1 over 2, 3 to 1 over 3, 4 to 1 over 4. Oh, there we go. Yeah, and this way you can see we've mapped n to 1 over n and shown that this set is also countably infinite. It has the same same cardinality as the natural numbers. All right. So we're going to do this question. I'll try to give an explanation of it, but it's kind of a hard explanation to give, and I think this YouTube video does a good job describing it. So I'll explain it, and then we'll watch the explanation one more time. But I want you guys to try it first. So is the set of rational numbers countably infinite? So rational numbers are numbers that can be expressed as a ratio between two integers, and we'll write it as a over b. And some examples are 1/2 and 3/5. You know, other examples are 1/3, 1/4, 1/5, 2/3, 2/4, 2/5, so on like that. So rational numbers are any number that can be expressed as a ratio between two numbers. And see if you can figure out whether these numbers are countably infinite. This is a hard question, so I'm curious to see what you think of it. So I have one yes and one no so far. I guess a hint on this is that it's going to be hard to use an expression for this. You know, before we use the expression to map the natural numbers to this set, we use 1 over n. It's going to be pretty hard to do that for this set. So if you're going to figure it out at all, if it is countably infinite, you're going to have to use the listing method. So figure out if there's a way to list the rational numbers in some order so that you'll list every single rational number. So I think I have like 3 no's and 2 yeses. That's exciting. So this turns out that the rational numbers actually are countably infinite. So that means that the rational numbers have the same size, the same cardinality as the natural numbers. And remember, that's going to be Aleph null. So let's figure out how to show this. So let's make a grid of all the rational numbers. So we'll start in our first row with 1 over every integer. So we're going to have 1 over 2, 2, is that right? That's not right. And then it's going to be, yeah, that is, let's see. We need 1 over 1 first, and then 1 over 2, and then 1 over 3, and then 1 over 4, and 1 over 5, right, and so on. And then our second row is going to be 2 over numbers. It's going to be 2 over 1, 2 over 2, 2 over 3. And you'll notice that, so 1 over 1 is actually the same as 2 over 2, but it looks prettier if you write it this way, so we're just going to kind of ignore And then we'll write 3 over 1, 3 over 2, 3 over 3. And I'm not going to write the rest. It's going to go on forever. And then it'll keep going forever this way as well. So this is a way we've sort of laid out the rational numbers in a grid. And then from this grid, we're going to see if we can find a way to list these in order. Because even if we can't find an expression, as we've talked about, if you can just find a way to list the elements of a set, it's going to be countably infinite. So what we're going to do is do sort of a snake pattern. And we're going to start with 1 over 1. And then from here, we're going to go to 1 over 2. And then move down the diagonals. So this diagonal. Now that we've finished this diagonal, we're going to go down to this diagonal. And then move along this diagonal. And then now that we finish this one, we're going to move over here. And in this way, we're going to sort of snake along like this. Yeah. And cover every single rational number. Because we're going to get every single ratio of 2 integers. And it's going to cover the entire grid. So hopefully that made sense. But it's a hard diagram to draw. So I'm going to switch to the YouTube video and we're going to watch that. And hopefully that clears up any confusion.
We can't hear anything.
I don't think you shared the sound.
Okay.
And it's really laggy.
Okay. Just do your best with it. Can you hear it?
If I grab these markers here, I also have...
Okay, I can hear it now.
Awesome.
And what I want to note is that I can come here in whatever order I so like, and I can line up that each marker is associated with 1 cup, each marker is associated with 1 cup, and that the number 3 is sort of independent of either of these objects. It's associated with the 3 markers or is associated with the 3 cups. And the fact that I can sort of line them up in this way doesn't matter. If you give me 3 of any objects, I can imagine lining them up in the same way. So what we really mean when we just say go and count something is that we really have the numbers 1, 2, 3, 4, and so on in our minds, and we want to line up the objects with those numbers 1, 2, 3, 4, and so on. Now this is a pretty elementary concept, but we're going to take that idea and extend it to infinite sets. For example, consider this correspondence. I'm going to send 1 to 2, I'm going to send 2 to 4, I'm going to send 3 to 6, and so on. Generally, I'm going to send n to 2n. This is some kind of correspondence between the positive integers and the positive even integers. Indeed, we can say that every single integer is associated with or corresponds to exactly one of the positive even integers. That indeed there's what we sometimes call a bijective correspondence between these 2 different sets. And what I mean by this is, first of all, every even integer is hit by something. Take the even integer 100, then 50 got associated to it. You take 102, then 51 is associated to it. But that it's only associated exactly once. There's only one number, 50, that goes and becomes associated with 100, not a whole bunch of different ones. When they have these 2 properties, sometimes called...
I'm going to pause it 1 second to let it catch up. I apologize if it's lagging. Hopefully you can see the important images at least.
1 to 1 and on to, we get this terminology of a bijective correspondence. Whenever you have this kind of relationship where everything in the first set gets associated with exactly one thing from the second set, that's how in mathematics we say that they're going to have the same size. And so in this case, the integers and the even integers, we will claim to have the same size. And while it might seem a little bit strange to be talking about the size of infinite sets, I want to note that this basic idea of trying to line all of the elements up and seeing that we have this correspondence between them, this is the same way that we worked in the finite case, that we could say that two different sets in fact have the same number because you can line them all up in this really nice way. So this is an appropriate notion that can be extended into the infinite case. So that was all very nice. We looked at the integers and the even integers, but now I want to look at an association between the integers and the rational numbers. I want to look at some way where I can have the same kind of correspondence, but they go from all of these positive integers into the rational numbers, where rational numbers are numbers like 3/5 or 5/7. Something where you've got an integer on the top and a non-zero integer on the bottom. That's what a rational number is. Now, the methodology is going to look a little bit like this. I'm going to write down first the number line, but I'm going to write it in a little bit of a strange way. So in this number line that we have here, we've got not 1, 2, 3, 4, but 1 over 1, 2 over 1, 3 over 1, and so on, which is just the same way. It's writing the number line in terms of a fraction. So now I want to make a sort of vertical dimension to this. I've written out the number line, the integers 1, 2, 3, 4 in fraction form, but now I'm going to go up 1 in the denominator. So I'm now going to go and try to look at 1/2, 2/2, 3/2, 4/2, and so on. So all the same numbers, but I've upped the denominator by 1. By the way, sometimes you get repeats like 2 over 2 and 1 over 1 are really the same number, but we're not going to worry about that. We're going to write down a few too many. That's going to be okay. All right, so then I'm going to do the same thing. Now it's 1 over 3, 2 over 3, 3 over 3, and so on, and I can carry on that progression. So really what I get here is this entire sort of plane of rational numbers. And indeed, you can think all rational numbers are here somewhere. Now, how can I line this up, this sort of two-dimensional thing, with the integers, which are sort of a one-dimensional thing? Because what we're trying to do is trying to get that correspondence where every integer gets mapped to some particular rational number, and every one of the rational numbers is hit by something. That's our objective here. So how can I do this? So what I want to do is I want to tell you a mechanism by which I can give you a first rational, a second rational, and a third rational. And what I'm going to do is I'm going to begin right down here on the corner, and I'm going to look at that 1 over 1. That's going to be my first rational I'm going to choose. Okay, next up I'm going to go and look at 2 over 1. That's my second rational. Now, if I keep on just coming along the line here, the problem's going to manifest itself, that I'm just going to get all of those ones of the form 7, 8, 9, 10, all the integers, but I'm never going to get around to a half because I have to go sort of on for infinity first before I can get up to a half. So I can't just go all the way along the line. So what I'm going to do is sort of snake around a little bit. The next one I'm going to choose is this one. I'm going to go and choose a half. So the first one is 1, the second one is 2 over 1, and the third one is 1/2. And then I'm going to go up 1, I'm going to go to a third, I'm going to go and snake around back to 2 over 2, and then just keeps on going, keeps on snaking around. And I think what you can see from this process, and I'll cut it off here, is that, in fact, I'm going to get to every one of these positive rational numbers eventually. This snaking process is going to keep on hitting them. If I can imagine it keeps on going up, my snakes get longer and longer as they go in these diagonal lines, but I'm going to hit every single rational number. But more importantly, is that I've done this in a way that has told you what the first rational that I'm going to hit is, what the second, what the third, what the fourth is, as in I'm sort of listing off and counting the different rational numbers. So if I clean up some space for it, what I've done is I've sent the integer 1 to 1 over 1, the integer 2 to 2 over 1, the integer 3 to 1/2, and the integer 4 to 1/3, and so on and so forth. Note that I might want to do some skips. So for example, where should we send 5? Well, if I look at my snake, it goes to 2 over 2. But since 2 over 2 and 1 over 1 are the same thing, I'll just discard that, and I'll just send 5 to the next one. 5 can go to 3 over 1. But the point is this. I've got this map from the integers into the rational numbers, and it hits every single one of those rational numbers. And so that is the sense by which I will say that the integers and the rational numbers, two infinite sets, have the same size, even though there are so many more rational numbers than integers. And to sort of illustrate kind of how remarkable this is, I want you to think about this. So here's the number line again, and I've got 0 to 1, some region here, and I've listed a whole bunch of different fractions, different rational numbers that are between 0 and 1. 1 over 1, 1/2, 1/3, 1/4, 1/5, all of those are between 0 to 1, and there's infinitely many of them. And all of them are going to squeeze in here between the integer 0 and the integer 1. And then likewise, I can change my numerator here. I got 2/2, 2/3, 2/4, 2/5, and so on. Another infinite list. There's some overlaps, but it's an infinite list, and all of those fit inside of there. And then, because I can do this by changing the numerator as much as I like, I actually have this infinite collection of these infinitely long lists, and absolutely all of them are fitting in between these two integers 0 and 1. So this gives you some sense of just how many more rationals there are than the integers, and yet they have the same size. Now, I hope you liked that video. We're going to have another one.
Let's see. All right. I hope you at least got to see the explanation of the snaking pattern pretty well. And hopefully that cleared up any confusion you had. Any questions about anything yet? So just to reiterate, I guess the sets we've talked about so far that have the same size as the natural numbers, meaning they're all countably infinite, and they all have the cardinality aleph null. These are the natural numbers, the whole numbers, the integers, the even numbers, the odd numbers, the rational numbers. All of these sets that we've talked about so far are countably infinite. You can list all the elements out. So now we're going to talk about bigger sets. So if aleph null sets are called countable, sets with more elements that you cannot make a correspondence are called uncountable. So these are sets that you can't list the elements, you can't make a correspondence with the natural numbers. They are uncountable. And then every single set is going to be either finite, meaning it doesn't have infinitely many elements, countably infinite, or uncountably infinite. And countably infinite sets or countable sets are the smallest infinite sets. There's nothing between a finite set and a countably infinite set. So one example of an uncountable set is R, the real numbers. And you can imagine the real numbers as basically all decimal numbers with any number of digits. And it could have, infinitely many digits in either direction, left or right. So 1 is a real number, 2.3 is a real number, 5.678 is a real number, this is a real number, pi is a real number, e is a real number. These are all real numbers. So we're going to show that the set of real numbers is uncountable using a proof called Cantor's diagonal argument, because a guy named Cantor came up with it. So for simplicity, we're just going to talk about the real numbers between 0 and 1. Because if a set has, if this set, that is just the real numbers between 0 and 1, if that set has more elements than n, then the real numbers will also have more elements than n. So by doing this one case, we can talk about all of the real numbers. So we're going to use a technique here called proof by contradiction, which means you assume something to be true, and then you show that there's a contradiction, so that assumption doesn't actually work. And so by assuming that assumption, and then showing that there's a contradiction, then you actually disprove the assumption. And so our assumption here is that there is some mapping between n and this set of real numbers. So if there were a mapping like this, then the real numbers would be countably infinite. So they would have the same size as n. But if we can show that there's a contradiction in this assumption, then we will know that R is uncountably infinite. So if we assume a mapping, we can sort of write it out in a diagram like this. So we would have the natural numbers in one column here, starting at 0, or they should actually start at 1 because they're natural numbers. And then they're going to go to infinity, or I guess all of the natural numbers, because yeah, they're going to go on forever. And then we're going to list out the real numbers here, and they're also going to go on forever. And so we've assumed that there's some correspondence here between the natural numbers and the real numbers. The problem is, if we can add a new number to this list that isn't in the column of real numbers, then we'll have shown that this list actually isn't complete. The mapping is not complete. So what we can do is we can move along this diagonal in the numbers that here are highlighted in red. So we'll take this 2, and we'll put it on the bottom. We'll take this 9. We'll take this 3, this 2, this 3, this 3, this 9, this 9, this 2, this 1, this 3, and this 2. We'll take all of those digits and we'll put it on the bottom. And then we'll change every single one of these digits. And we're going to do this out to infinity. And in doing so, we've created a number that is different from every single other number in the list. So we took this 2, we changed it to a 7. Now our new real number is different from the first real number. Then we took this 9, we changed it to a 4. Now this real number is different from this first real number, or I guess the second real number. And then we took the 3 here and changed it to a 6. Now it's different from the third one. And by doing that forever, we've made this new real number that's different from every single real number. So we've shown that giving any such mapping, right, even if you pretended that a mapping did exist, we can always add a real number that is not in the list. And because of that, no mapping can exist. And because no mapping exists, there are more real numbers than there are natural numbers. It has a greater cardinality, and thus it is uncountably infinite. So the natural numbers are countably infinite, R is uncountably infinite. And it has more elements. It is a bigger infinity. And the same guy has another video about this, and I think it's a good one also. So we're gonna watch that one, and then I don't know if we're gonna have time for code after that. We will see. All right.
In the first episode of my new cool math series, we looked at integers, numbers like 1, 2, 3, 4, and rational numbers, numbers like 3/5 or 5/7. And we said that these two infinite sets actually have the same size. And what we meant by that, what we meant by saying that infinite sets have the same size, is to say that there was some function from the integers to the rational numbers where every rational number got hit exactly once. And that this notion of a bijective function is what we meant by saying that these two different infinite sets have the same size. So now the question is, what about comparing something like the integers and the real numbers, where the real numbers are those that have things like pi and e and root 2 in them? And what we're going to find out in this video is that in fact, those two different infinite sets, the integers and the real numbers, do not have the same size. And the argument we're going to be using is one that is due to Cantor, and it is a very famous diagonalization argument, and I'm going to show it in this particular video. The idea is this. Let's not try to compare to all real numbers. Let's just look at the real numbers that are between 0 and 1. And if it was the case that the integers and the real numbers had the same size, then we could find some function. We could line up the integers and the rationals, and we could pair them in this bijective way. So what I'm going to do is I'm going to try to list all of the different real numbers. Let's just make an infinite list. There'll be a first, a second, a third, and a fourth lined up with the first integer, the second integer, the third integer, and the fourth integer. Now, I'm going to sort of make up which of these real numbers I want to go first and second. They could be anything. How about the first one could be 0.1? That's a real number in between 0 and 1. I'm actually going to go and write it in terms of its decimal expansion after the 0 point. So this looks like a 1 first, and then all the rest zeros. 0.1000. Okay, how about for the next one? I'll do 0.333333, a decimal expansion for a third. That's another real number. Then I can do 0.1415926535897932, which is the first bit of the decimal expansion for pi minus 3. It's just kind of fun. I'm just putting some random ones in there. How about 0.99999, so on. This is a decimal expansion for the number 1. And then I'll fill up with 1 7s, 2 7s, 3 7s, and 4 7s, which have some cool patterns. You can see how that works. But the point is this, I've just chosen these at random. You could choose whatever ones you wished, and any other real number that you might imagine we're going to suppose could occur on this list. Now, what I want to argue is that no matter how you did it, no matter what choices I made or what choices you made for how we tried to line up the real numbers and the integers, no matter how we did this, that we could not get all of the real numbers. So now I want to draw your attention to these so-called diagonal entries. It's looking here at this first digit, the 1/10 spot, in the first particular row, the first real number we've identified, and then it's going to go down and it's going to go and look at the second digit in the second real number, the third digit in the third real number, the fourth digit in the fourth real number, and so on. It's this diagonal that we have here. What I'm going to do is I'm going to make a new real number that tweaks along this diagonal. So the 1 that we have here, I'm going to go and change that 1 and make it a 2. Then I look at the 3 that we have, that's in the second row in the second location, and the 3, I'm going to add 1 to it and make it a 4. The 1, I'm going to go and add 1 to it and make it a 2. The 9, I'm going to add 1, but instead of making it a 10, I'm going to cycle around and make it a 0. So the 9 is going to become a 0. The 5 is going to become a 6, the 4 is going to become a 5, the 4 is going to become a 5, and the 7 is going to become an 8. And what we have here is a new real number. This real number is not on the list. It's different from the first one, it's different from the second, it's different from the third. So no matter how you went about choosing your list of real numbers, we can always construct this new real number that's different from whatever listing you might have given. And so this tells us that it is not possible to find a function from the integers to the real numbers that has this property that every real number gets listed exactly one time in association with the integers. There's not a bijective function between them. And so what this says in truth is that the integers and the real numbers, that they have a different size, that you cannot align them in this way. Now, we have some terminology for this. When you have an infinite set and you can line it up with the integers, where there's a first, a second, a third, and so on, we're going to say they're countable because you can align them with the counting numbers, and there's a fancy math symbol called Aleph naught for it. And so what we saw in the first Cool Math Series video was that the rationals were countable. They were Aleph naught because you could line them up in this way. You could say that there was a first, a second, a third, and a fourth rational number. And that was the construction we gave. But here in this video, we've shown that you cannot do that for the real numbers. No matter how you try to line them up, this Cantor diagonalization argument destroys the ability to make them countable. And so we say that this set is uncountable.
All right. Let's see. So hopefully that was helpful as well. All right. Okay, so that was pretty perfect timing. This is the last slide, and then we'll have time for a few minutes of it. So just to go everything we just talked about. Real numbers are an uncountably infinite set, and they have cardinality Aleph 1. The real numbers have more elements than the natural numbers, the integers, and the whole numbers. And in this process, we've also learned that there are different sizes of infinity. So some infinities, like the number of elements in R, are bigger than other infinities, like the number of elements in N. I will get the Kahoot set up in the meantime. Let me know if there are any questions about anything at all that we went today. There we go. guys can join in. We don't have a lot of time to join, so I'm going to give you guys about a minute to join so we can get started. All right, I'm going to start it in like 20 seconds. Get in if you can. If you can't, it's no big deal. Just do the questions. You don't have to do it on your device. You can just watch and say what you think the answers are. All right, let's get started. Oh, exactly. This symbol is aleph null, the Hebrew letter aleph, and then that 0 means null. Yeah, so which of the following is the cardinality of the natural numbers? That's aleph null, the smallest infinity that you can have. So this, if you put infinity, you're sort of correct in that the natural numbers have infinitely many elements, but in math we write it as aleph null. So the natural numbers, we just said they're aleph null. Another word for aleph null is countably infinite. So they are not uncountably infinite. Uncountably infinite is bigger than countably infinite. Yep. So the real numbers are a set that's bigger than the natural numbers, and they are uncountably infinite. And I think this will be our last question. Yep. Which of the following sets has a different cardinality than the others? N, W, and Z are all infinite sets, and they are countably infinite, while 1, 2, 3, 4, 5 is a finite set. So it is not infinite. All right. That is all we have today.